Welcome to Lesson 3 of Puzzles to Exercise the Mind. How many ways are there to arrange the three boxes in a row? We have three distinct boxes, A, B, and C. Think about that for a second and we'll give you the answer on the next slide. We have a solution here to our problem. It's 6 possibilities. Let's go through them. So we can start with an A, and then we have two choices for how we arrange B and C, either ABC or ACB. Then we take B, and then we can do A and C in two different ways. And then C, and pick C is going first. Then we can do AB or CBA. So 6 different solutions. It doesn't have to be letters. It could be numbers. It could be different objects. The point is, if you want to arrange 3 distinct objects in a row, like we have here in a linear fashion, then there's 6 ways to do that. If we had only 2, there would be 2 ways. You can see that was the way we've embedded the second 2 positions here. It's B, C, or CB. So in general, we'll see when we have more objects how this works. This is normally written as 3 factorial. That's 3 times 2 times 1. That's a common notation when you're talking about permutations. These are permutations, by the way. That's the term that's used here when you have different orderings of distinct objects. So let's make the problem a little bit harder. What if we have 4 boxes? How do we arrange those in order as we've shown here? And before I give you the answer, you may want to think about reducing this to the problem of arranging 3 boxes in a row, and then maybe just add another box and use that to find the solution. So I mentioned on the previous slide, we can reduce the problem to the 3-block case. What we do is we take one block, let's say it's A, and then we have the other blocks B, C, and D, and we have 6 or 3 factorial ways to arrange those. And then we can take B and put that off to the side, and then arrange A, C, and D in 6 ways. And then we do it for C, and then take the other 3, and then D, and then take the other 3. So basically we have 4 choices here, and then 3 factorial or 6 choices here. So the answer is 4 times 3 times 2 times 1, which is usually written as 4 factorial, and that's 24. And you can see how this would go to 5 and 6 and so on. If you have n distinct objects, I should have put the word distinct in here, and you want to put them in a row, line them up as we've shown in the case was just 3, so one after the other. And then the answer is 1 times 2 times 3 times n, or you can write that as in shorthand as n exclamation point, which is read n factorial. Let's change the problem around a little bit. The first few combinations we looked at, we had the objects in a row. What if we put them in a loop, as in a charm bracelet, for example? How many different ways can you put 4 different objects to create distinct charm bracelets? So the trick here is that if you rotate this, for example, 90 degrees, then you would have B would come here, C would be here, D would be here, and A would be here, and that would really be the same bracelet. So we need to take that into account when we compute the number of distinct arrangements in this loop or cycle configuration. So looking at the configuration on the left, where we have A, B, C, D, that's the same as just rotating it to the clockwise, and you have the A, B, C, D. It's the same thing. Then you have A, B, C, D. So these 3 are the same. And then again, you can move A one more. You get A, B, C, D. So you have 4 what would be four different things when we were talking about just putting them in a row. They combine to just a single charm bracelet, right? It's just turning it on your wrist, and it would be the same configuration. So as I note here, the above configurations are all the same. The 4-row configurations are different, and they would all map to this same loop here. So I was just showing it in terms of symbols, A, B, C, D, and then you kind of move the A over one, and you put the D at the beginning, and then you move A out again, and you put B at first, and then you just push it out one more time and put A at the beginning. So what we need to do is to find the number of possible loops with 4 objects, and that would just be the 4 factorial that we found when we put them in a row, and then we'd have to divide by 4 because each one is equivalent to 4 configurations when they're in a row. So you have to divide 4 into 4 factorial. And in general, if you have n distinct objects, then there's n minus 1 factorial loop configurations or cyclic configurations, however you want to term this. And another way of looking at it is people sitting at a table, and there's nothing specific about the chair or anything. It's just, a totally symmetric table. Chairs are all the same, and you're only concerned about who's sitting next to who. So you might want to figure out how many combinations are in that case when you have 4 different people, and that would be 6. There's 6 ways of sitting people at a table. And in fact, that's the more common way this problem is presented. How many different ways of sitting people at a table? The one thing you need to be careful is when you word it that way, if the one chair is, say, a special chair that's, I don't know, larger than the other chairs, and maybe one is smaller than the other chairs, and the other 2 chairs are all distinct, then you're kind of back to the original problem where the chairs are distinct, but that's not the idea. The idea is just completely symmetric table, the chairs are all the same, and you're only concerned about where people are sitting relative to each other. So we have now 2 ways of counting things, and we're going to use that for some of the problems in terms of probabilities, which we'll talk about coming up next. Let's talk about probabilities. The discrete probabilities, where you have a finite countable number of outcomes, are typically computed by looking at the total number of outcomes and then dividing that into the number of possibilities for the event you're interested in. So let's try to clarify that with some examples. So you have, what is the probability of rolling a 2 on a die and getting a heads on a coin flip? So I'm going to solve these in the next few slides. I'll just read them off to you here. But we basically have 2 independent events, rolling the die and then flipping the coin, are independent. And when you have that, you multiply the probabilities together. So we have another one that's similar. What is the probability of rolling a 7 using 2 different dice, or equivalently rolling the same die twice and getting a 7? So again, these would be 2 independent events. What is the probability of randomly drawing the ace of hearts from a deck of cards? So to do this one, we need to know the total number of ways of drawing a card from a deck, and then we just have this one event here, this ace of hearts. What is the probability of randomly drawing an ace from a deck of cards? So similar to this, but now, of course, we have 4 aces. Then the last one here is a bit harder. What is the probability of being dealt 4 of a kind from a deck of cards? And this is a reference to a poker hand. So you're dealt 5 cards, and the question is, what's the probability that 4 of them are the same? And of course, there's only 4 of each kind in a deck, so the 5th card would have to be something different. And I just give an example here. 4 cards of the same value in any other 4 cards, such as 4 kings, and then say the jack of clubs. That would be one possible way of getting 4 of a kind. Okay, so you may have done these, or at least some of these in your head already, but we'll talk through them and just try to illustrate some of the principles of probability. And then we'll have some more difficult problems after this. So our first problem was the probability of rolling a 2 on a die where you have 6 values on the die, 1, 2, 3, 4, 5, 6, and getting ahead on a coin flip. So we have multiple probabilities here, and they're independent events. So we multiply. As I mentioned in the previous slide, we multiply the two probabilities. So the probability of getting ahead, of course, is 1/2. You get either head or tails. And then you do the roll the die, or you could do it at the same time. The assumption is they're independent. And the probability of getting a 2 is just 1 out of the 6 possibilities. So you have 1/2 times 1/6, and you get 1/12. So the more things you add to this, the probability of taking another die and rolling that and getting a 1, for example, that would be 1/6, and then you'd have to multiply that times the 1/12. And you can kind of see the intuitive nature of that. As you string together more and more independent events, the probability that all of them will happen becomes less and less. And the next problem is, what is the probability of rolling a 7 using 2 dice? So we have 6 ways of getting a 7. We can have a 1 and a 6, a 6 and a 1. So these are different because this is dice number 1, this is dice number 2. And 2, 5, 5, 2, 3, 4, 4, 3. So there's 6 ways of getting a 7. And the total number of ways of outcomes for rolling 2 dice, you have 6 possibilities on one and 6 on the other. So the total is 36. And then to get our probability, we just divide by the number of ways of getting 7, divided by the total number of possible dice rolls, and we get 6 over 36, or 1/6. And that's, if you know anything about rolling dice, that's the most probable roll that you get, 7. If you take, you may want to try as an example 5, you're going to get fewer possibilities here. To roll a 5, it's either 1, 4, 4, 1, 2, 3, 3, 4. So there's only 4 cases here in that for getting a 5, and then you would have 4 divided by 36 in that case. The probability of randomly drawing an ace of hearts from a deck of 52 cards. So the total number of possibilities is 52, and there's only one ace of hearts, so that's 1 over 52. That's a pretty easy one. Probability of randomly drawing an ace from a deck of 52 cards. Well, there's 4 aces, so it would be 4 over 52, or 1 over 13. What is the probability of being dealt 4 of a kind from a deck of cards? So there are 13 ways to get 4 of a kind. It's, the 2s, 3s, 4s, all the way up to Jack, King, Queen, and Ace. So there's 13 ways to get 4, the card that's going to be 4 of a kind. Then once you get your 4 of a kind, the other card, there's 48 cards left now in the deck, and so there's 48 ways of getting the 5th card. So the probability of getting 4 of a kind is 13 times 48 divided by the possible number of 5 card hands. Well, we don't know what that is yet. You may know what it is, but I haven't explained it yet. So I need to explain how to get how many different 5 card poker hands you can get out of a 52 card deck, and then that would get divided into 13 times 48 to get our probability. So let's talk about that next. So to solve our last puzzle concerning the 4 of a kind, we need to figure out how many ways of selecting 5 cards from 52. And we'll talk about it in terms of an example, or we'll use a simpler example. But this is known as a combination. If you have a set of distinct objects and you want to draw a subset out of that, of a smaller number of those objects, and it's called a combination. And we'll look at an example where we have 7 distinct objects and we want to choose a set of 3. We don't care about the order, so you can think of the numbers from 1 to 7, and we want to pick 3 numbers out of 7. So 234 is the same as 432 because we don't care about the order. You think about a poker hand, we don't care about the order. The cards are just dealt to you face down. You pick them up and you don't care which card you got first or second. It's just the set of 5 cards. So keep that in mind. Okay, so let's work our problem for 7 distinct objects, and we want to draw out 3. So look, just looking on the bottom here, the first choice, we have 7, so we pick one of the 7 objects. That leaves us with 6. So we have 6 choices for the next slot, so to speak, and then we have 5 choices for the third slot. So that gives us 7 times 6 times 5 choices. However, as I mentioned, we don't care about the order. Just going back to our card example, if you dealt 5 cards, you don't care which card you got first in your hand. The order doesn't matter. So there's 6 possible ways of rearranging the 3 that you picked out of the set of 7. So we need to divide by 6, or 3 factorial. So our answer is 7 times 6 times 5 divided by 3 factorial, or 6. And sometimes that's written this way here. The 4 factorial divided into 7 factorial, the 4, 3, 2, and 1 cancel out. I know that looks a little bit obscure just in the context of what we're discussing here, but the formula of choosing k objects, out of n distinct objects is normally written this way here. It's written n choose k, and the solution is n factorial over n minus k factorial times k factorial. Okay, so now we have our formula, and on the next slide we'll apply that to our card problem. So recall from the four of a kind hand in poker, we determined there were 13 ways of getting the 4 of a kind, and then 48 ways of getting the 5th card, but we didn't know what the total number of hands were, and now we know it's 52 choose 5. It's a big number. There are tools on the internet. If you look up combinations, I'm sure you'll find an online app that'll do this computation. It comes to 2,598,960, and then this product on the top is 624, and that's about 0.0024 or 0.024%. So very, very slim possibility, and anyone who's played poker knows that that doesn't happen very often. And I'm just writing out the formula here. So 52 choose 5 is 52 factorial over 52 minus 5 factorial times 5 factorial, and this of course is 47. And then the 47 and the 52 factorial mostly cancel, and you're just left with 48, 49, 50, 51, and 52. In fact, you could do this just on a calculator. You just need to multiply these together and then divide by 5 factorial, and you could even do some cancellation here. You could divide the 5 and the 50 and get 10, and the 4 into the 48, and the 3 into the 52, and then multiply out what's left on the top and divide by 2. So here's our answer in terms of the number of possibilities, and then this is the associated probability of 4 of a kind. Some of the other poker hands are also have probabilities. They're a little bit harder to compute. We'll look at a few of those also. You'll see that a lot in probability textbooks. They'll use poker hands because it exhibits a lot of different things that you need to know in terms of combinatorics and probabilities do the computations. I have a few more probability problems for you to look at. We'll do these in the following lesson, so I'm just going to give you the problems here with a little bit of explanation. First one is, what is the probability of a full house in a 5-card poker hand out of a 52-card deck? So that's 3 cards of one kind and 2 cards of a different kind, like 3 jacks and 2 5s would be an example. The next one is, what is the probability of a straight flush? So there's cards in order, like 2, 3, 4, 5, 6, and they all have to be either a heart or a club. So they have to be the same suit. And you can use an ace as either a 1, so you could do 1, 2, 3, 4, 5, or you could use it as a card superior to the king. So it'd be 10, jack, queen, king, and 1. That would be another straight. And then again, they'd have to be all the same suit, to hearts, clubs, spades, in diamonds in order to be a straight flush. And then the last one is, what is the probability of a straight, and excluding the straight flushes. So you need to, once you count the number of straight flushes, you need to subtract that from the number of straights and then divide by the total number of possible poker hands. And we'll talk, as I say, we'll talk about this. I'll give you an answer on the next lesson. One thing you might want to experiment with is some of these artificial intelligence applications on the web are pretty intelligent. If you copy what I've written here, you may very well get a correct answer. So one possibility is GPT. There's Gemini from Google. The Bing has one, and Bing Chat, I believe it's called. And then there's other ones you may know of. So not just for here, but you would be surprised. Some of the puzzles I'm bringing up here, if you actually asked an AI application, it would give you a pretty good answer, and with an explanation in most cases. Let's have a look at what's called the prison problem. We have a prison, and the warden has decided to make a special offer to release a group of 10 prisoners if they all succeed in a particular task. So the key word here is all. They're going to each be given a task, and if all of them succeed, then they all get released. So each prisoner is assigned a number from 1 to 10. The way I saw this puzzle originally was there was actually 100 prisoners, but I think 10 is enough to illustrate the point. And in a room, in a locked room, there are 10 boxes numbered 1 to 10. Within each box is one coin having the number of one of the prisoners. However, the box number and the number of the coin within do not necessarily match. In fact, the coins are randomly assigned to the boxes. So prisoner goes into the room and he sees 10 boxes, and he's going to be allowed to open 5 of them. If his number is in any one of those 5 boxes, then that's considered a success. So the problem is, or the difficulty is, that all 10 prisoners need to do this, and they can only open 5 boxes. So there's a bunch of conditions here that'll make it more difficult. It's basically a logic puzzle. So there's no way of the prisoners communicating once the process starts. So just to go through it, the first prisoner goes into the room. He opens 5 boxes. If his number is in one of those 5 boxes, then he's counted as a success. Then the next prisoner goes in, and if he finds excuse me, his number in one of the 5 boxes, then that's a success. So it has to happen 10 times in a row, and each time the prisoner goes into the room, opens up the 5 boxes, he's going to be left out through another door. He won't be able to communicate with the other prisoners, and the room is returned exactly as it was. So there's no way of leaving marks on the boxes or turning the coins a particular way or leaving a mark on the floor. There's no possibility of the prisoner leaving any information once they get outside once they're finished with their opening up their 5 boxes. And again, the boxes are closed, everything's returned exactly as it was, and then the next prisoner comes in. So the only thing afforded to the prisoners is before this process starts, they can communicate. If possible, in fact, there is a strategy, but which I'll give you when I talk about the answer in the next lesson. So they can't communicate beforehand, but again, once it starts, they go into the room, they open 5 boxes, they find their number, it's a success, they leave the room, no information is left there, everything is returned exactly as is, and the next prisoner comes in. So they need to have 10 successes. It's like flipping a coin 10 times in a row and getting 10 heads in a row. So very unlikely to achieve this prison release without any particular strategy. So we have a picture here of the inside of the room. There's the 10 boxes, so the numbers are on the boxes, 1 to 10, and then there's a coin in each side, inside each box, and the coins are what would correspond to the prisoner. So if prisoner number 9 went into the room and he opened box 1, 2, 3, 4, and 5, he would get a failure here, failure here, failure here, failure here. But then when he opened box 5, there would be a 9 in there, so that would be considered a success. He's only given 5 choices. He leaves the room. All the boxes are shut. The coins are left where they were, unmoved, and the next prisoner comes in and has the same task presented to him. So as I mentioned, the probability is like flipping a coin 10 times and getting heads or tails, the same outcome. So it's basically 1/2 to the 10th power, and that comes to 0.00977. So very small probability without any particular strategy. There's a very small probability the prisoners are going to win. And as I mentioned, the puzzle was what I saw was originally posed with 100 prisoners. So then the number is just astronomical. It's pretty much 0 to get for all the prisoners to succeed. However, and this is why the puzzle is interesting, there is a strategy that these prisoners can devise beforehand that gives them over a 35% chance of winning. So that's the interesting part. It's not easy to guess at this, and in fact, the person who created this puzzle didn't know the answer, and he found it through some mathematical research paper, and it's quite fascinating. So we'll talk about this in the next lesson. You might want to give it a try, but again, the important point is the prisoners can only communicate before this starts. They have no means of any type of communication or leaving information in that room. Once they leave the room, it's back exactly as it was beforehand. So you may want to think about it. It's quite ingenious, and again, we'll talk about it in the next lesson. On this slide, we have something called Pick's theorem. It's not a puzzle, but something I thought you might find interesting. First, let me say that we have an example here, and this grid highlights integer points. So wherever these lines that are along integer numbers here, 1, 2, 3, going horizontally, and same thing going vertically, all these intersection points are called integer points. So for example, this point here is the x value is 1, the y value is 2. So these are called lattice points, and the puzzle is really about finding, or not the puzzle, but the theorem is about finding the area of a polygon based on its the integer points interior to the polygon, as well as the vertices of the polygon. So here, these are the conditions that we need to have in order to apply the theorem. The polygon needs to have all its vertices at integer points, at lattice points, which is the case for our example here. And in that case, we let I be the number of interior integer points. So the red points in our example, these are each at a lattice point, and B be the number of integer points on the boundary. So the vertices have to be, by the condition of the theorem, they have to be integer points, lattice points. And then sometimes when you're crossing between two vertices, you'll hit another lattice point, and here we see it's 1, 1, so we have to include that in our computation of B. And then in that case, the area of the polygon is I plus 1/2 B minus 1. So let's look at our example and see if we can compute the area based on this theorem. So first, the interior integer points, 1, 2, 3, 4, 5, 6, 7, 8, 9. We got 9, and then boundary points, integer boundary points, 1, 2, 3, 4, 5, 6, 7, 7 over 2, and then subtract 1. We get 23 over 2, or 11.5 for the area inside of this based on the theorem. We can check our theorem by computing the different triangles and squares. So if we take, I'm drawing very roughly here, but if we take this triangle here, it's got 1, 2, 3, 4, 5. It's the base is of length 5, and the height is of length 1. So you have 5 times 1, or times 1/2. Excuse me, and that's the area of a triangle, right? 1/2 the base times the height. So we get the area of this triangle. Then we can come down here and do this one, and I'm putting the results here. So this 5/2 was this one here. Now we're working on this one. So this has height 1 and base 2, so that 1/2, 1 times 2 is at 1. Let's go to the next one. We'll do the square. Again, my hand isn't that steady here with the mouse, but this is 2 by 2, so we get area 4 for the square, and then we have this triangle here that has height 2 and base 2, so that's 1/2 times 2 times 2, that gives us 2. And then this last triangle is base 2, height 2, and again the area would be 1/2, 2 times 2, that's 2. You get 2 plus 2 plus 4 plus 1, it's 9. To 18 halves plus 5 halves, so 23 halves. So it did check out. We get the same area as we got when we used the Pick's theorem. And this will hold for any polygon that has integer vertices. Let's try a logic puzzle. In this puzzle we have knights who always make true statements, and they're not necessarily male, they could be a female. So we have knights that always make true statements, knaves that always make false statements, and spies that they can make either true or false statements. Okay, so there's a lot of puzzles of this type where you have knights and knaves, and sometimes they'll have a third type which can either tell the truth all the time or lie. Tell the truth in some instances and lie in other instances. And sometimes different terms are used for this third type here. So we have 3 people, Abner, Bertha, and Connie, are one of each type. So one is a knight, one is a knave, one is a spy. And they make 3 statements here. Abner says that he is not a knight. Bertha says she is not a spy, and Connie says she is not a knave. So who is who? How do we identify these 3 people with these 3 types? Okay, let's see if we can solve this. So Abner said he is not a knight, but knights always tell the truth. So in fact, if he was a knight and he couldn't make the statement that he's not a knight. So Abner is not a knight. We can make that conclusion. But if Abner was a knave, and knaves always lie, then the statement that he's not a knight is a true statement, in which case we have a contradiction. So he couldn't make that statement if he was a knave. And so we've eliminated 2 out of the 3 possibilities. So Abner, in fact, is the spy. And since we were told that there's only one person of each type, we've kind of eliminated one case. So the other 2 people are either a knight or a knave. They can't be a spy. Bertha says she is not a spy, which is necessarily a true statement, right? Because Abner is the spy. So whether you're a knight or a knave, if you make the statement you're not a spy, that's a true statement. And so that means that Bertha must be the knight. And then, of course, that leaves Connie as the knave, the liar, because there were only 3 possibilities. So there's actually several puzzles like this. There's a logician, Raymond Smullyan, who I quite like. He's written many books. He was writing into his late 90s. He's passed away a few years ago, but he wrote several books just on this type of topic, where he starts off kind of easy, and then he gets more and more difficult puzzles where you start getting really confused trying to work through things. And I'll put a link to at least one of his books about knights and knaves in the description to this video, and you might want to have a look at them. In fact, the books are quite inexpensive, and I think at this point they've sold so many. There's probably on Amazon, there's probably like used versions which you can get, almost for a few dollars. So definitely worth having a look if you're interested in this type of puzzle. Really test your mind without getting into a lot of complicated mathematics, but they're still difficult puzzles. We have another puzzle here. I'm calling it flipping bits. I initially saw it as flipping wine glasses, where you flip them from being up to down, but I thought it'd be a little easier for me to draw with just binary numbers. So you're given the binary number 1, 1, 1, 1, so 4 ones in a row, and you go through a series of rounds where you have to pick 3 of these and flip them to 0. So you can pick the first one, say the third one, and the fourth one, and flip them to 0. And then you go to the next round, and what's left, that you take that binary digit, and you have to pick another 3 and flip those from 1 to 0 or 0 to 1. So you have, on each round, you take 3 of the 4 places and change them from 1 to 0 or 0 to 1. And the question is, how many rounds does it take to get from our starting point 1, 1, 1, 4 ones to 4 zeros? So if you want to give this a try, pause the video here, and then I'll explain it on the next slide. We have 2 solutions here on this slide. I'll start with the one on the left. We hold the 1 fixed, and we'll switch the 3, 1, these other 3 ones to 0. So I put the one that's being held fixed in each round as red. So we have the 1 gets mapped to 1, and then the 3 ones to 0. Then we hold the second bit fixed and shift the other ones from 1 to 0, 0 to 1, 0 to 1, and the 0 stays fixed. Then we hold the third bit fixed and shift the 0 to 1, 0 to 1, 1 to 0. And then we hold the 0 fixed, and then it's pretty easy. We just have these 3 ones, and we shift those to 3 zeros. So you can do this in any order. The key is just holding a different bit position fixed in each step. So here we held the third position fixed, then the second, the first, and then the last digit here fixed. And you can see, if you follow through the details, we end up with all zeros again. So we could have done the second one, then the third one, the fourth, and then the first, and that would have also worked. You may want to try that. Okay, so let's look at this more generally on the next slide, where we have n digits, and a binary number with n bits in it. So here's the general problem. We start with n bits, and we require n minus 1 flips from 1 to 0 or 0 to 1, depending on the state of the binary number. And then in that case, a solution is possible when n is even, but not when n is odd. That's not obvious. It takes some work to prove that, and I'll give you a reference on this. So the procedure for n even is similar to what we did for case n equals 4. We just, on each round, we hold one of the bits fixed, and then we shift the other ones from 1 to 0 or 0 to 1. And we do that for each position, each bit position. And so it takes actually n steps to do that. So you might want to try it for n equals 6, the next possible case that has a solution. The problem I saw was from Minor Decisions. He does a lot of nice logical and math videos, and the particular video was called "This Logic Puzzle Stumped Chat GPT. Can you solve it?" So the author of this video put the problem, stated the problem to Chat GPT, and it didn't get it correct. I found Chat GPT to be pretty good actually with math problems, but apparently it didn't do well in this case. So this is a YouTube video. I'll put the link in the description so you can just click on it. And he goes through the case n equals 4, and then he actually proves that it's a minimum solution, and then he proves that for n equals odd, there's no possible solution, and he demonstrates that the solution for n being even. So it's a good video. It gets a bit technical in terms of the proofs he gives, but he does a good job in going through it slowly and explaining it pretty well, in my opinion.